And so we projected these smaller vectors up onto the surface, and then those vectors that we learned from way back from when we were talking about tangent planes, we ended up scaling it. And so now that it's scaled, it's the appropriate size, because we're talking about shrinking the delta x's and delta y's, or finding more partitions, and then that's going to be your Riemann sum. But we want to add up these areas, and if you cross these two vectors, you're going to get the vector perpendicular to it, right? But if you take the magnitude of that, it turns out that that's going to be the area of the parallelogram. So that's where we were. Here we go here. Area of parallelogram. Is going to be the magnitude of the cross product. And it doesn't matter what order we do this cross product in. Oh, can you see that? It doesn't matter what order we do this cross product in, because we're going to take the magnitude anyway. So remember, the difference between crossing it one way versus another way will give you a negative vector. But if you're going to take the magnitude, it doesn't matter which direction it's going. You're just going to measure its magnitude. So we've crossed this before, and it turned out to be either, whichever way we cross it, it's either fx, fy, and -1, or negative fx, negative fy, and -1. Yeah?
That's the vector for going up from that green plane.
Yeah, well, I don't want to commit to it, but it's either going up that's perpendicular, or it could be going down, as long as it's perpendicular. Right? And again, it depends on which way we cross it, which at this point I'm saying it doesn't matter. Yeah, so we're finding a little piece of area here, and then we're going to put that in an integral to find the area of the whole thing, the whole surface. Yeah. And so one of the things that we can do is that there's scalars here. This was scaled by delta x and delta y, and those scalars, when you're inside of the a magnitude and you're taking the cross product, there's some properties that we did, or at least we talked about, where you can take the scalars out. And so you take the scalars out and you get the magnitude of the cross product. And the magnitude of this is, regardless of which way you cross it, it's fx squared, fy squared, and 1 added together under a square root. So that's your big formula. And the delta x and delta y would have been just scalars that we would have taken out. So you put this in a Riemann sum, you add up an infinite number of these things, and then it becomes a double integral with the dx and the dy over the region. So that's where the formula comes from. And this idea of using the normal vectors for this is going to come back to us when we start looking at other types of integrals, because there will be other types of integrals beyond our double and triple integrals here. We're not going to cover quadruple integrals, if that's what you're looking at, but it's a different type of integral that's different from these two. All right, so the formula. That Riemann sum essentially becomes this. So it's a fx squared, fy squared, and 1 dA, which is either dx or dy, and depending on how you approach it. All right. So now you know the formula. We can just do a couple of examples. So what example are we going to do? Let's pick one example from here. Let's do one with a triangle. Example, the part of the surface z is equal to 1 plus 3x plus 2y squared that lies above the triangle with vertices at 0, 0, comma, 0, 1, and 2, 1. So I'm not going to care how this is going to look like in 3 dimensions. It'd be nice if you want to, but we can take a look at this, how this looks like in over its domain. So over its domain, we have vertices 0, 0, 0, 1, and 2, 1. So we have a region defined here, and just like setting up a regular double integral, instead of integrating this function, instead of just plopping this function down as your integrand, you're going to find the surface area formula for that. But to set up the integral, you're still going to do the same thing. You're going to look at this two-dimensional region and then try to figure out how to set this integral up with respect to x or y first. So I'm looking at this. If I go, here are a couple of options, and this is where I would encourage you to, we have a choice here, and we could do either way, and either way would probably be just as easy. But I noticed that if I go with respect to y first, I'm going to hit a function down here, and I'm going to hit a function up here. And the function down here is some line that I have to find, and some function up here is y equals 2. Okay, so look at that and say, oh, okay, that sounds fine, we could do that. But if you go this way, you're going to hit this first function over here that you're going to hit is 0. And when you're doing integrals, 0 is a nice set of limits to have, because usually when you plug in 0, it becomes 0 unless you're dealing with some other function. But that's highly encouraged to try to work with it that way. So that's what we're going to do. We're going to integrate with respect to, I drew that line parallel to the x-axis, so we're going to integrate with respect to x first. And so as we integrate with respect to x, you draw some random line. You can draw a bunch of them just to get an idea of what's going on, but just one representative line, and then you ask yourself, what x equals what is a I don't want to say function, but it's the graph that you want to enter into the region, and that's x is equal to 0 right here. And whatever this line is. Is it? 1/2 y. All right, so the other thing that we need to do is we need to figure out what this line is equal to, and we could do that y equals mx plus b business if you want. So b is 0, that's the y-intercept, and the slope goes rise over run, so 2 steps in the run and then 1 in the rise, so that's 1/2. Or you can use the 2 points, find the slope kind of business. Anyways, whatever you do to solve for this, this is how you would find the equation of the line. And then here, we need an x limit, so I'm going to want to solve for x. And that's going to be your limit for the inside integral. And then the outside integral, remember, are always constants, so y is going to go from 0 to 1. Okay? All right, now let's deal with the integrand. The integrand is going to be some derivatives. So let's see, z sub x with respect to x is 3. Z sub y, the derivative of this with respect to y is 4 y to the first power. So you throw that into the formula. You got fx squared plus fy squared plus 1. Then probably wouldn't hurt to simplify. We got 16y squared plus 10 all under square root. That's looking for some trig substitution business. Yeah? Oh, yeah, good idea. If we integrate with respect to x first, which is what we have in line, then that's going to give us, I'm still not going to do it. That's going to give us a nicer integral to deal with. All right, so let's finish this off. We set up our integral. The inside integral is going to go from, well, let's put the integrand in first. 16 y squared plus 10. And then we're saying that we're going to integrate with respect to x first, and our x limits go from 0 to 2 pi, or 2y. And then our y limits or constants go from 0 to 1. And if you do this integral, like Harrison said, if you integrate with respect to x first, this is just going to be x times this, and then a simple u substitution will get you the rest of it. Okay? Should I find answers for these? I think you guys could do it. And if you can't do it off the top of your head, I think you should practice doing it, because integrating is important. You should know how to integrate, especially if you pass Calc 2. But like I said in the beginning of the course, I expect you to know how to integrate, and whether you do or not, I don't care. So I think it would be a good skill for you to try this at home. Oh, I have some visuals I want to show you in a little later. So we're going to integrate. Where's my size? Just to get the answer. Was it 2y? And then the square root of 16y squared. Let's use a nice font typesetting. that right? So like I said, something that could be done using just a simple integral and a u substitution. And again, I encourage you to practice taking integrals. For the sake of being able to take integrals. I mean, in reality, when you ever have to do this in, like you're working in industry or whatever, and you're a physics person or an engineer person, for some reason you need an integral, you just plug it into Mathematica or plug it into MATLAB or something, and then cranks it out for you. But I think it's a nice party trick. You can go to parties and say, hey, I can integrate. Get really hooked up and tell somebody you can integrate. All right. Oh, so visuals. I wanted to show you the visuals using, I found this, an old thing that I had. So the idea is to basically, slice this up into little partitions and then find little areas. And so here it looks like I have 8 partitions. We're going to go 8 by 8 on that surface, on that saddle. And then here are your tangent lines and your tangent vectors, your curves on the surface and your tangent vectors. And then just randomly taking a look at it, it's hard to see, but there's one little square there. And then if you get a whole bunch of them going, you get this. I think it might be easier if we take away the surface. And so if you look at it, it just looks like oh, I changed it. This is 10 and 20 now. Let's go really rough approximation. So if I just have 4 partitions, this is what I have, just a bunch of Post-its. Okay? And so you can imagine that if you were to find the areas of these things, it's not going to give you a very good approximation, but it's some approximation. But the more you cut it up, the smoother it's going to be. And so this almost looks like it's the whole surface, but really if you take a close look at it, there's little holes and gaps because these are just planes that are trying to mimic the surface. Anyways, that's a nice picture. So let's do another example. And I think for the next example, I saw a good one from your homework set. We have a hyperbolic paraboloid that lies between 2 cylinders. New page. So hyperbolic paraboloid is that same one that we've been looking at, and maybe the signs are switched. But we have 2 cylinders, and that's what we want to focus on. And so on the xy plane, you look at x squared plus y squared is equal to 1, and x squared plus y squared is equal to 16. So we have a couple of circles, radius 1 and 4, and then the region that we're integrating over is an annulus. Now I can attempt to set this up in x and y, but already I kind of don't even want to try, because this would be an ideal situation to use polar coordinates, right? So we're going to use polar coordinates instead. And the way we're going to do that is we want to represent polar coordinates in terms of r and theta. And most of the time we're going to have r go first, and theta would just sweep around as constants. Because r has more of a chance of being a function than theta. So the r is going to go from a radius of 1 to a radius of 4. And then theta goes from where to where? 0 to 2 pi. Whoa. 0 to 2 pi. Okay? So that's our setup, and then now we need to figure out what our derivatives are so we can set up the integrand. And our derivatives will probably look like zx is equal to negative 2x, and zy is going to be positive 2y. Not that it matters, because we're going to square it anyways. So the integrand will be negative 2x squared plus 2y squared plus 1. So it looks like it's going to be 4x squared plus 4y squared plus 1, all under square root. Now, since we're moving towards polar coordinates, you probably would be looking for the x squared plus y squared, so that you can change that into r squared. Okay, so the integral setup is going to be your double integral, and your integrand is square root of 4r squared plus 1. And remember that when you changed into polar coordinates, the Jacobian or the differential that pops out is an extra r. And then you're going to integrate this with respect to r from 0 to 1, or from 1 to 4, and then theta from 0 to 2 pi. Okay? Any questions? So, can you picture this? How does this thing look like? It's a rectangle. What?
That's right. So typically when you draw this rectangle on the y-axis, the left edges, in this case it would be opposite.
No. What? Close. No. This is a paraboloid. It's a hyperbolic paraboloid. So it's that saddle. Let's see. I'm going to attempt to draw a saddle. So that's the saddle, but it's not doesn't have a square base, right? It has a circular base, so we need to cut it with a couple of cylinders. Wow, that doesn't help. So imagine how that would look like. Whoa, whoa. I have a picture of it. It's actually a little bit different here. We need to go from radius 1. So here's a domain, which is the annulus, and here's a saddle, but the saddle has a hole in it, and you're looking at the saddle from a roundabout way. So that's the surface that we're looking for. Pretty cool, huh? All right, let's get a picture of it and put it in our notes so that our notes look nice and pretty. Okay. Yeah, that's all there is to this this section. Any questions? No? All right, let's move on. So our next section is oh, I was going to do this. This is intersecting cylinders. Maybe I'll assign that for extra credit. But our next section is triple integrals, so we're on the 3 integrals now. So this time, we're looking at a volume for your region. You're integrating over a volume. It's a solid thing that you're integrating. And that, in terms of the geometry of finding areas and volumes, it seems kind of weird to think about it that way. And so we're going to talk about this, and maybe the first application we're going to talk about would be like a density. So here's a definition that we could try to rederive, but we've been deriving stuff and getting kind of old. It's not old, it's fun. But don't drink and derive, that's not good for you. So the idea is that now you have a triple element that you're integrating over, and you're integrating over a volume. So it's kind of hard to think about this, to make sense out of this. And like I said, the best way to start thinking about triple integrals is maybe to think about density. So as just a quick application or a quick setup for what triple integrals might be used for would be a density. So suppose the density function of a solid is given by some rho function, and the density is given as a kilograms per cubic meter. And so when you're talking about a density is kilograms over cubic meter, it's a density of a solid. So if you imagine, I don't know, something solid, hot chocolate. You got some hot chocolate, you stir it up, and then you leave it alone. You know how it just kind of, the chocolate just goes down? So you stir it, leave it alone, you put it in the freezer, and it becomes solid. And so the density of that is going to be thicker down in the bottom than it is up on top, right? So we can define that as a density function, maybe just a simple function of z. You can really, this is an example for Calc 2, because you can do this in 2 dimensions, because the slices are going to be like just circles if you slice up the frozen hot chocolate from a cup. Unless you put it in a strange solid. Never mind. So anyways, that whole idea is like a density function, and so to find the mass of that chocolate, or the hot chocolate that's not, I guess it's frozen now, frozen hot chocolate, then you would multiply the density times the volume. And so that's how we can think about this as a density function. Solid, let's give it a name. I think they use, I don't know what they use in the book. I think they use E. I don't know why. Maybe it comes after D, which is what they use last. Sometimes they use omega, but that's too hard to write. Yeah. That's cooler to write, though, so maybe we'll do that sometimes. Anyways, then the mass is given by, well, it's going to be a triple integral over E of your rho function. And then the delta x, delta y, delta z that you would multiply it by is summarized into a dv. So whenever you see dv, think about that as dx, dy, dz. Just like when you think of dA, you think about that as dx, dy. Just a little aside, dA equals dx, dy in whatever order is convenient. And then so now dv is dx, dy, dz. It could really technically be any variable, x, y, z, or u, v, w, or something, rst, but we see, more often than not, we see x, y, z. Okay? So now the trickiest part here is to think about this as trying to find the volume in 3 dimensions, to think about this as you know, I've been saying with double integrals, you don't really need to see things in 3 dimensions. It's a little bit more difficult to not see things in 3 dimensions because you're forced to try to imagine the solid, right? And so you're kind of somehow forced to look at it in 3 dimensions. But what I want you to do is think about this going from 2 dimensions to 3 dimensions. And then once you think about it in 3 dimensions, briefly, your problem is going to get flattened down to 2 dimensions. Okay, and then it becomes a 2-dimensional problem. And thinking about this in 3 dimensions, for those people who can't if you guys have a hard time visualizing things in 3 dimensions, then just try to imagine functions, generic functions, and then you really need 2 functions to look at, something above and something below that would encompass the solid. Okay. For what that's worth, let's see if we can think about doing a problem. So the first couple look like they got the integrals set up for you already. So let's do something more interesting here. Maybe like 19, 20, 21. And I'll start with number 19 and we'll see where we go from there. So in this example, it's looking at a tetrahedron. Remember what a tetrahedron was? It's a four-sided pyramid-looking thing. A tetrahedron enclosed by the coordinate planes in the plane 2x plus 2y plus z is equal to 4. So what we want to do is, again, it's hard to think about this. Imagine how this thing might look like. But with the tetrahedron, it turns out that you can actually, I think you can graph this. So let's see about graphing it. Especially when they say coordinate planes. When you see tetrahedron with coordinate planes, you know that 3 of the 4 sides, tetrahedron is a 4-sided polygon. So 3 of the 4 sides are going to be the xy plane, the yz plane, and the xz plane. So you got the 3 sides already kind of covered here. And so to just imagine this 4th side, which is a plane, right? This is a plane. Ax plus by plus cz is equal to d. So to try to figure out how this plane looks like, what we can do is we can find the x, y, and z intercepts. Where is it going to intercept the x-axis, the y-axis, and the z-axis? So let's think about the x-intercept. So where is it going to hit the x-axis? What can you say about the x-axis? What can you say about values of the x-axis? That would be a plane line. What? No. What would be equal to 0? The other variables would be equal to 0. So if I want the x-intercept, think about setting the y and the z equal to 0, because that's on the x-axis, right? So 2x plus 0 plus 0 is equal to 4. So if you set y and z equal to 0, you're going to get x is equal to 2. So that's going to be your x-intercept. And then you do the same thing to find the y-intercept and the z-intercept. And then you get 4 and 4. And then from there, you just draw that triangular-looking thing that might resemble your tetrahedron. Okay? Now that you have the tetrahedron, just like in double integrals, when you're trying to figure out the limits, that's what we need to do. We need to integrate with respect to one of the variables first. And in this case, you can really integrate with respect to any variable, but I think we tend to want to integrate with respect to z first. in general, just so we can look at the XY plane after we do our three-dimensional stuff. Okay, so let's say we want to integrate with respect, we want to set up our limits. So integrate with respect to z first. So if we integrate with respect to z first, we imagine this solid region. We want to draw a line parallel to the z-axis going through the region. So what we're going to do is we're going to imagine this thing going through the region, just like, you know, we imagine the other one going through the region, except now this is three-dimensional region. And we imagine this thing parallel to the z-axis from the negative to the positive. And then we're going to hit a couple of surfaces. One of them we hit when we get into the region, and then the other one we hit when we get out of the region. So the question is, when that happens, what two surfaces are we hitting? The first surface, pretty easy to get. So it's the xy plane, so z is equal to what on the xy plane? Z is equal to 0 on the xy plane, right? So now you hit the xy plane, and then you're going to be inside of the region, and then eventually you're going to get out of the region. And what function do you hit when you get out of the region? The surface, the plane, that other thing. This thing, yeah. But it's you want it to be a function of, not a function of z, but you want z as a function of the other two variables. So you want to solve for z here. So 4 minus 2x minus y. Okay? So that's going to be our z limits. Now, this is a triple integral. We got one limit. This is going to be the innermost limit. But now we need to set up a double integral on the outside of that to figure out the rest of this. So what we need to do, since we took it with respect to z first, our next step is now to consider an xy plane and to try to see what this region is on the xy plane, the shadow that this solid is going to make on the xy plane. Now, according to this graph, my purple region here crosses the x-axis at 2 and the y-axis at 4. So now it becomes a two-dimensional problem where you can decide to integrate with respect to x first or y first. And in this case, either one would be just as easy. So we could do it with respect to y first. Let's draw a line parallel to the y-axis, and then you can ask yourself, what functions do you enter and exit? Y equals what? So the first one, again, is fairly easy. It looks like it's going to be y equals 0. And then you exit out of this function. Well, that's this function over here, which is this plane when z is equal to 0. So you can set z is equal to 0 there and solve for y. Or you can use the point slope formula to find the equation any way you look at it. So I think if I solve for y, y is equal to, this has a slope of -2 and a y-intercept of 4. And that's like setting z equal to 0 here because it's on the xy plane, z is equal to 0. So if you set z is equal to 0 here and solve for y, you're going to get the same thing. And that would be my upper limit for my y. I guess I'll put 4 minus 2x. Doesn't matter. And then the last limits, you got 2 down, 1 to go, and the last one's always constant. And you can look at your two-dimensional drawing there, just go x is equal to, where do you start and where do you end? That's it. You guys written 3 integrals all in a row like this? Something kind of exciting about it. We don't have a function. Maybe write it from left to right, or right to left. Okay, so we got 0 to 4 minus 2x minus y. Our y goes from 0 to 4 minus 2x, and then our z, or our x, sorry, goes from 0 to 2. All right? So we have begun. Yeah.
So like, just related, you got a pretty easy way of doubling those because this is getting volumes out of sort of integrated two-dimensional areas. Now we're integrating three-dimensional areas, and we're getting, like, is there any more physical relevance? Like, we're getting this extra variable out of it.
Yeah, well, that's why I went with the, that's why instead of geometry, I kind of went with the whole mass idea.
Right.
Yeah. But mathematically, you can think about this as a four-dimensional volume. If your mind can go to this four-dimensional space where you can imagine four-dimensional beings and things, then you can certainly find volumes of four-dimensional things. Those would be called hypervolumes.
The volume is like variable quality inside the kind of.
That's not variable. It's all just, you know, instead of having 3 dimensions, it's 4 dimensions.
It's non-homogeneous in this physical instance where you put this hot chocolate, right? The density is not homogeneous.
Yeah, right.
The quantity is the non-homogeneous.
Yeah, so that's the fourth variable. All right. See you guys next time.
Are we done this section or continuing on it tomorrow?
Oh, we're going to do more.
Okay, I was like,